Hello, my name is Bernard Brault. I'm with OTN Systems, and today I want to give you a short demo about IEEE 1588 transparent clocking and what it does for on an Extran network. So let's start with a little bit about describing what 1588 is. So what you have is somewhere probably in your control center or a couple of strategic location. You may have a Grand Master clock, something of a high quality clock with a high precision, and you will have several boundary clocks in your substation finally driving because of application that require precision timing within the microsecond inside the substation. And in between you will have a network, and 1588 is about synchronizing clock over a terrestrial network. These clocks obviously can be synchronized also over GPS, but GPS is not necessarily a reliable source, and you want to make sure you have a terrestrial backup over your microwave or packet network. And I'm going to show you what transparent clocking can do in this circumstance. So the demo I'm going to give you is six Extran nodes, and the two end nodes that you see right here, I will have a master clock connected to this particular node at the end right here, and a slave clock on the other end, and there'll be a service in between. And the service is a 1588 streaming service that master and slave clock communicate over, and that's what basically does the synchronization, where the slave clock will try to synchronize the master clock with the level of precision within the microsecond or better. So as you can see right here, we'll establish a 1588 Ethernet service. The bit stream here is fairly small, so it's somewhere around 30 kilobits per second. A number of messages are exchanged between the master and the slave, and they're essentially trying to figure out what is the latency between the two of them and correcting the slave clock so that it can synchronize microsecond precise to the master clock. And in parallel with this, I will establish a disturbance traffic with a traffic generator. And the traffic generator is going to inject a fairly large amount of larger frames in this hop right there, and the idea is to create a certain amount of disturbance. The 1588 service will have higher priority, but even though it has a higher priority, 1588 packets that are trying to egress on this specific port right there, they're not necessarily competing against the disturbance traffic, which is a lower priority, but you may have a packet from the disturbance packet that's actually currently egressing on the port, and that could be jumbo frame or a larger frame, and the 1588 packet has to wait for that to egress, and it creates packet delay variation. Once you pass this node here, you no longer have to worry about disturbance traffic, at least not from this source right there, maybe from other source in your network, and then it flows through the slave. But when the slave responds back, you have the same situation that's happening at this particular port right there, where again, you know, your 1588 packets are I wouldn't say competing, but queuing up behind egressing frames. Of course, as soon as the egress frame comes out, being a higher priority, it will be the next one to be served, unless you have some TDM services at a higher priority and so on. So that's what I'm going to show you. Let me go to the live view right now. So what you see here is TXCare NMS showing a live view of the Extran network that I have. Highlighted here is the master clock is connected to the interface 1 port 4 of node 5 right there, and the view of the master clock is shown here. It's a NetProbe 2000 and it has a setting for 1588, and it's currently provisioned as a master clock. And then at the far end, connected on node number 6 here, interface 1 port 4, is again another NetProbe 2000, but this time around it's connected as a slave. And let me show you the setting for the disturbance traffic. So I have another Ethernet generator that's connected here, and it generates frames, goes across to a reflector, and the reflector sends the frame right back. So I will have a bidirectional traffic flow here of about 700 some megabit per second compared to the 1588 here that's much smaller. Another way to look at it is if I click on the fiber here, what you can see right there on that fiber is you see the small skinny 1588 traffic flow, and you see the larger disturbance. Currently the disturbance traffic is provisioned, but the traffic generator is not enabled. So going back to the network view, without any disturbance traffic, let's take a look at the master and the slave clock. So I go to the result, look at messages. As you can see here, the master is sending and receiving from the far end, and on the slave side, let's take a look at the graph. And what you see on this graph is deviation or offset from the master in nanosecond. So what you notice right there is that the slave is within somewhere around 600 to 700 nanoseconds, so that's 0.6, 0.7 microsecond off from the master. And this is with transparent clocking not enabled on the X-Strand. Alright, so and I can show you the traffic for this and the disturbance. So let me show you this. Here's a performance view. What you see on the top right there is the traffic flow that on X-Strand for the 1588 between the master and the slave, and at the bottom down there is the disturbance traffic that has not been started. So let me start some disturbance. I'll bring that here, and what I'm going to do is start a disturbance flow. And you'll notice right away that as we're injecting somewhere around, as you can see here, 600, 700 megabit per second of traffic. Notice that the scale here on the slave has changed, and now the disturbance is plus minus 40,000 nanosecond. That's 40 microseconds. So this clock here is offset from the master plus minus 40 microsecond. And that means that your clock is no longer microsecond precise at this stage. So if I stop the disturbance traffic, disturbance flows right back down, and the clock starts stabilizing again. And you'll see that it'll go back to stabilizing like the flat line there that was like when it was within a microsecond. Here it's going back to within a microsecond. So all of this was without 1588. So the next step that I'd like to show you is enabling 1588, and I could go across all the settings. In order to enable 1588, you have to enable it on every port and every device that's involved in transporting traffic between the master and the slaves or the boundary clocks. I'll use a script for this. So it says enabling 1588 on all the nodes, and I'll just run the script. And the script is running, so let me just move this out of the way, and it's currently loading the script. It says wait a little bit. So during the enabling, we're losing traffic here. Notice that the 1588 flow between the master clock and the slave clock has been turned off, and as soon as the loading of 1588 is done, enabled, it will come back. Just give it a minute or so, and we'll see this when it starts seeing a response right here. Should be about right there. There you go. So we're starting to see traffic flow between the master and the slave. Slave will start resyncing, and then they'll start, converging back into There you go. So now the offset from the master, and it'll start stabilizing. So I'm going to pause the video for just a minute, just to give the slave a chance to synchronize, and then we'll come back and show you what it looks like without disturbance traffic, but now with transparent clocking enabled. Okay, I'm back, and what you see here on the screen now is with transparent clocking enabled on all the ports and the devices, the X-Tran device, involved in the transport of the traffic flow between the master clock and the slave clock. What we're seeing now is that the slave clock is offset to the master plus minus somewhere around 20 nanoseconds, right? So previously, if you remember, even without any disturbing traffic, mind you, there's always a little bit of traffic from NMS, from Discovery, and so on. We had like 200-300 microseconds, even more than that, close to a little sub microsecond, but this was like much higher. Now the slave clock is within 20 nanoseconds. So let's take a look at the impact of turning on that large disturbing traffic, because that simulates pretty much real live traffic that you will have on your network. So let me turn on the large disturbing traffic, and you will see here that it rises to 700 or so megabits per second, large frames, and notice on the right it has no impact. So transparent clocking not only improved the stability or the offset from the master on the slave by a factor of 10, but it remains stable with disturbance traffic, so it's not affected by traffic. Well, thank you very much for watching. I'll be doing probably a follow-up video on this, maybe pushing it a little bit more, where I'm going to have multiple nodes in between and show you how far we could push this. And if you're interested to learn more about transparent clocking on your X-Tran network and about the power profile of 1588, please give us a call, and thank you very much for watching.